Hi, everybody. I hate that it does this and keeps changing it so you see the picture of my kid in front of the my house. But we deal with what we got to deal with here, so let's take a little look-see. And welcome to, this is Mr. Folly. Whoa, my goodness. Welcome to 3.1, starting a new exciting unit about covalent bonds. I know, I can't wait either. So, covalent bonding is the only type of bonding we're going to talk about here. Now, what's weird is if we talk about only covalent bonding, we have to compare it to some others. So you will hear some others mentioned, but covalent is the focus of this unit. So, describing covalent bonding. So, first of all, forming bonds releases energy, so it is more stable and favored. So, things have bonds. Oops, don't do that to me. So, what that means is, here, oops, is expect bonds. All right, expect bonds. Barf, seen it before, we'll hear it again. Breaking bonds absorbs energy. Hey, look at that. Breaking absorbs. Barf, releasing energy forms bonds. Hey, barf, releasing forms. There you go. All right. Covalent bonds are between two nonmetals, so we know where that is in the periodic table. Easy peasy. Electrons are shared between two different atoms, and this is called directional because it's shared between exactly two. Here's hydrogen all by itself. Oh, share. Look at sharing electrons. Carbon dioxide, oh, share. The prefix co means to share. Oh, share. Let's cooperate. Oh, we'll share the operations. Oh, share. We can live in a commune. Oh, I see co there. And we could all live together. Oh, share. So covalent bonding fills the octet. So what we learned from last chapter is we would gain or lose electrons to fill the octet. This is different. We're going to share to fill the octet. So look at CO2 above. Carbon started with 4 electrons, okay? So here's 1, here's 2, here's 3, here's 4. But it's going to share 2 electrons from this oxygen and 2 electrons from this oxygen. So 4 plus 4 is 8, okay? So it now has 8 and it's filled valence shell. CO2 above shows that each oxygen started with 6, so let's see if we can do that. I'll change my color to a happy red. 1, 2, 3, 4, 5, 6. And you see how these 2 electrons right here are 7 and 8 that the oxygen takes. Electrons in a double bond count. They count for, electrons in bonds double count. They count for both oxygen and carbon. So I'm going to draw this a little bit differently. I'm going to do a CO. So remember, these bonds, let me erase it and put it a little prettier, right here, are really 4 electrons, right? So carbon counts this. If I'm carbon, I'm counting 2, 4, 6, 8. Okay, there's carbons. And do you see that if I'm oxygen, I'm counting 2, 4, 6, 8, and that counts for both of them. Okay. Covalent compounds form molecules. So I just want to emphasize that covalent compounds form molecules. So what that means, it has a distinct beginning and an end. Oh, look how this has its own special little shape, okay? That means it's not going to be a lattice like this. See how this one can go on forever and be super repeatable? So not this. Not covalent. Okay. Physical properties of covalent compounds. Okay. So covalent compounds have low melting points and low boiling points. So the attractions between those molecules are weak. Now, I said that, and I said they're low, but it's worth noting that all states of matter are possible. Now, when I say butter, you don't go, oh, man, that's something that lasts forever and doesn't melt. butter's pretty easy to melt, right? So I know that some people melt butter just by shoving it under their armpit and waiting for it to melt. It's not my favorite way, but I've heard of it done before. So butter is a solid. Liquid is, well, water is a liquid, and oxygen is an example of a gas. Covalent compounds never conduct electricity. This is the best way to identify if it's covalent or not. Physical properties, when they're solid, they're dull, not shiny, not lustrous. Remember, we struggled with the word lustrous, which means shiny. Only polar covalent molecules dissolve in water. We're going to get into what polar means, right? And they're brittle. All right, let's name some stuff. Nomenclature. We're going to name covalently bonded compounds. So notice it's going to start with a non-metal. Okay? So it's going to start with a non-metal. And then we have to learn these prefixes, right? Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hex is 6, hept is 7, oct is 8, non is 9, dec is 10. Okay? So, I'm going to cough here. So we're going to use the prefixes, and we're going to make the last word end in "ide," which we did that last unit a little bit, and sound good. There's also no mono on the first element, and we never have the elements OO or AO. So, for example, CO is an element, well, we know CO2 is carbon dioxide. CO is carbon monoxide, not carbon monoxide. So that's kind of silly. All right, so let's take a look here. SF6. First element, no mono. So I'm going to say sulfur. Sulfur. So I have 6 of them. Hexa, sulf, make it end in ide. There you go. Next one. I got 2 of these. Di-xenon. 8. Octa, bromide. Got to end in ide. S4O9. 4 is tetra. Sulfur. I thought I didn't have the first one. The first one you don't use for mono only. Tetrasulfur. 9 is nona oxide. There's no AO, so it's nonoxide. Okay. Flipping it around, these get really easy. Trinitrogen monosulfide. Trinitrogen, hey, that's trinitrogen. Monosulfide, that means 1S. Hexasulfur, sulfur, hexa, 6. Dichloride. 2 chlorines. And this one doesn't do it because sodium's a metal, and I tried to trick you. I so tried to trick you. Did it work? Did it work? Did it work? Okay, so we're not going to do sodium dihydrogen phosphate because it starts with a metal. All right, polar covalent bonds and polar compounds. Polar is stronger than nonpolar. So if I have a polar bond, I'm comparing to a nonpolar bond, polar bear wins. Polar bears are the strongest bears. I don't know if that's true, but we'll go with that. Polar means ended. North Pole, hey, here's the globe. North Pole, hey, here's north. South Pole, hey, that's south. That's an end. Okay. Polar bonds have a positive and a negative end, indicated by a delta positive and a delta negative. Polarity occurs when the electronegativity difference is significant, and that's from 0.5 to 1.9. Okay. Your periodic tables have electronegativity values on them, the original ones I gave you. Electronegativity is found in your periodic table. I'm giving you a new periodic table. It's got this stuff on here. Electronegativity is going to be 2.2 here, okay, for hydrogen. So you should be able to find hydrogen and see that it's 2.2 on the periodic table you have from me. Electronegativity is the ability to attract bonded electrons. Hey, I know that. So more electronegative atom will be delta negative. Electrons are negative, it's going to be more negative. Determine if it's polar covalent or not, show the deltas. So nitrogen is 3.04 and fluorine is 3.98. So the difference there is big enough. So that's going to be polar. And fluorine has the bigger number. So I'm going to draw an arrow and point it at fluorine. I'm going to put delta negative and delta positive. You don't need to do both, but that's it. C to H. H is 2.20. Carbon is 2.55. 2.55 minus 2.20 is nonpolar. Oxygen, whatever its number is, it's subtracting from itself. It's going to be 0. Mg and I. Mg is 1.31. Mg is 1.31. and iodine is 2.7. Notice how these are absolute values. So that's going to be 1.4. So that's not going to be polar, that's going to be ionic. So let's see if I can get my thing to move here for my electronegativity values. Oh no, I lost my number. I saw it before. Oh, 0.5 to 1.9. So this one is 1.4, so it is polar. Okay. Now I don't like this because polar bonds should be between two nonmetals. All right. Non-polar covalent bonds and compounds. Non-polar covalent bonds have perfectly even sharing, electronegativity difference of 0.4 or less. Okay. No poles, so I do not draw deltas. Also, no arrows. The lowest melting and boiling point. They never conduct. They do not dissolve in water, but they do dissolve in other nonpolar liquids. And they are weaker than polar. And that is it. We've learned all we need to know about covalent. To that, I will say,